it became very clear that the limiting of CO2 emissions would require a transformation of the global energy system. We would need to somehow generate between 100 and 300% of all the energy that people consume right now from a source that didn't emit CO2 into the atmosphere, between 20 and 60 times as much energy that we're going to need from some source, let's call it source X, in 50 years. That's an unprecedented technical challenge.
There are no earthly technologies now online or capable of coming online by 2050 that can solve the world energy problem. The most promising long-term nuclear power source is fusion. Fusion, as opposed to fission, does not require dangerous heavy elements. Fission breaks apart two heavy isotopes, releasing energy.
And in fusion, we're actually fusing together, that is pushing together, very light elements, and usually isotopes of hydrogen or helium. What we'd like to do is to produce fusion energy and have very little or no radioactivity left over. We tend to look at fusion in three different generations. The first generation is the fuel cycle deuterium and tritium. Deuterium is a naturally occurring isotope of hydrogen, sometimes called heavy hydrogen, that occurs in all water all around the world. In fact, everybody has deuterium in their body. Tritium, on the other hand, is a very rare isotope which is radioactive. If we talk about the second generation, the deuterium helium-3 reaction, it's a very clean nuclear reaction. If we look at the third generation fuels, which are even harder to make fuse, we can look at the helium-3 cycle, that is fusing two helium-3 atoms. That is a perfect nuclear cycle because there is no radioactivity associated with that nuclear energy release. We can actually release nuclear energy with no nuclear waste.
The waste from the helium-3 reaction is hydrogen and helium. You can use the hydrogen as fuel by burning it with oxygen in fuel cells. The waste from that reaction is water. To get rid of this waste, you can bathe in it, sprinkle it on your flowers, or make tea.
There is a lot of helium-3 in the universe, and certainly in our sun, but there's very little helium-3 on the Earth because the helium-3 that originally was captured on the Earth has all diffused away up into the atmosphere and out into outer space. The big problem we faced was that we didn't know where to find large amounts of helium-3. Well, in 1985, our entire Fusion Technology Institute group went off on a retreat, and we sat around for 2 or 3 days trying to find out where we could find large amounts of helium-3. And then almost simultaneously, two of our scientists, Dr. Leighton Wittenberg and Dr. John Santarius, came up with the idea that, well, the sun is the biggest fusion reactor in our solar system, of course, and the biggest producer of helium-3. Helium-3 is actually manufactured in the sun and leaves in the form of solar wind. Solar wind, being charged, is deflected by all bodies that have magnetic fields and is absorbed in the upper atmosphere by all bodies that have an atmosphere. And if you look at the various bodies starting from the sun out, Mercury has no atmosphere, but it has a magnetic field. Venus has no magnetic field, but it has an atmosphere that's very, very thick. The Earth, we have both, and you can march your way all the way through the solar system and come to the conclusion that the only large body near to the sun that has neither a magnetic field nor an atmosphere is our moon. And the consequence of that is that the solar wind then is deposited in the surface of the moon and has been for over 4 billion years. The moon has been hit with about 500 million metric tons of helium-3. Then the question is, how much of that helium-3 still is on the moon? In January of 1986, we went down to the Lunar and Planetary Institute in Houston, and we looked through the books of all the Apollo missions and the analysis of all the rocks that had been brought back. And lo and behold, all the rocks that were analyzed had helium-3. Well, that made us very happy, but we weren't quite sure that what we were reading was correct, so we walked down the street, literally, to the Johnson Space Center, and we talked to some of the space scientists, and we asked them if what we had seen and what we had concluded was true, and they looked at us and said, sure, but so what? They had known about helium-3 since 1970, but didn't know what it was good for in terms of nuclear processes. We had known helium-3 would be a good fusion fuel, but we didn't know where to get it. Of the 500 million metric tons that hit the moon, there's still about 1 million metric tons on the surface of the moon. Helium-3 has been buried very, very shallowly in the surface of the lunar regolith, that is the very fine-grained material. And it's very loosely held, such that if you heat the lunar regolith, the lunar sand, up to temperatures like 600–700 degrees centigrade, most of the helium-3 is evolved. It would be relatively simple to extract the helium-3, purify it, and liquefy it, and bring it to the Earth. And then one might ask, well, how much is it worth? If we were to have oil cost $28 a barrel, that makes the helium-3 worth about $4 billion a ton, or about 40 tons of helium-3 would provide all of the electricity that we need in the United States. About $160 billion worth of helium-3, that's about what we spend today in fuel. If there's 1 million metric tons on the moon, that would last the Earth, the entire Earth, for thousands of years. 1 to 2 space shuttles a year would provide all the helium-3 we need to make all the electricity in the United States, to replace all the coal-fired plants, all the natural gas plants, all the hydroelectric dams, all the nuclear fission plants, all the windmills and all the photovoltaic systems. And in fact, we now have a steady-state fusion device operating at the University of Wisconsin using deuterium and helium-3, producing a steady-state power of about 1 milliwatt. Now that's not very much, but it's a very small device and a very inexpensive device. If we can make a small portable source of neutrons that could be very beneficial for things such as treating cancers, detecting clandestine materials such as explosives, chemical weapons, fissile material in small packages that could be of vital importance for homeland security. If we bombard materials that have long half-lives on the order of 1 million years or more with high-energy protons that would come from the, say, the D-helium-3 reaction, we could convert those long-lived isotopes to very short-lived isotopes and have them decay away. We could also use those protons to destroy fissile material, that is, material that could be used for weapons. Then we can completely remove the generation of radioactive waste from our concerns. That is, we could have nuclear energy without nuclear waste. And that is the pot of gold at the end of the rainbow.